All right, I had a bit of a disappointing morning, which led me to getting on late here. So that's a big bummer, but I am here, and I'm going to make some progress on this chapter, last section of the chapter, floating point code. I guess my motivation was not really there for this section. So I gotta find my curiosity. So let's look through the pages here a little bit. Just scan through here. So we get to learn about the registers, the SSE and AVX registers that are used for floating point. That's pretty cool. And then we start going into some of the instructions with code examples. So these are kind of like, oops. These are like move instructions. These are some type of these are wordy, but I'm sure there's some type of like reason to the madness. So VCV TSI to SS. So it's DQ. It's a double to quad. Single, double, quad. Seems like that's the, and then I for signed, or is I for integer? Okay, some more code examples. Disassembly of the code. Some little exercises. More code examples and disassembly. Or am I going backwards here? Yeah, I went backwards. Here's some bitwise operations, comparisons. Okay. It doesn't really scream at me like super interesting, but I'm gonna try to stay motivated on this. Let's try to stay interested, and we'll see how it goes. One technique I was thinking about doing is just do all the reading and then go back and do the actual problems. I might do that this time. Just focus on the reading and then come back and complete the problems. Alright, so the floating point architecture for a processor consists of the different aspects that affect how programs operate on floating point data are. The floating point architecture for a processor consists of the different aspects that affect how a program operating on floating point data are mapped onto the machine, including how floating point values are stored and accessed. This is typically via some form of registers, XMM and YMM registers on AMD 64. The instructions that operate on the floating point data, the conventions used for passing floating point values as arguments to functions and for returning them as results, the conventions for how registers are preserved during function calls. For example, with some registers designated as caller saved and others as callee saved. To understand the x86-64 floating point architecture, it is helpful to have a brief historical perspective. Since the introduction of Pentium MMX in 1997, I was 12 years old. Both Intel and AMD have incorporated successive generations of media instructions to support graphics and image processing. These instructions originally focused on allowing multiple operations to be performed in a parallel mode on known as single instruction multiple data, or SIMD. In this mode, the same operation is performed on a number of different data values in parallel. Over the years, there have been progressions of these extensions. The names have changed through a series of major revisions from MMX to SSE for streaming SIMD extensions. MMX is like multimedia extension, I think. And most recently, AVX for advanced vector extensions. With each generation, there have also been different versions. Each of these extensions manages data in sets of registers referred to as MM registers for MMX. Let's ask AI real quick. What does, I think it's multimedia, does MMX stand for in Intel? Multimedia extension? Yeah, okay. XMM for SSE. Okay, these extensions manage data in sets of registers referred to as MM, registers for MMX, XMM for SSE, and YMM for AVX, ranging from 64 bits for MM registers to 128 bit for XMM and 256 for YMM. So for example, each YMM register can hold either 32-bit values or 64-bit values, where these values can be either integer or floating point. Oh, it must be a ZMM. Sorry, let's go back here. Where does XMM and YMM come from? Yeah, AVX 512 has ZMM. continue reading. Starting with SC2, introduced in the Patent 4 in 2000, the media instructions have included ones that operate on scalar floating point data. Using single values in the low order 32 and 64 bits of XMM or YMM or ZMM registers, this scalar mode provides a set of registers and instructions that are more typical of the way other processes support floating point. All processes capable of executing x86 64 code support SC2 or higher. And hence, x86 64 floating point is based on SZ or AVX, including conventions for passing procedure arguments and return values. Our presentation is based on AVX2, the second version of AVX introduced with Core i7 Haswell processor in 2013. GCC will generate AVX2 code when given the command line parameter mAVX2, code based on the different versions of SSE, as well as the first version of AVX is conceptually similar, although they differ in the instruction names and formats. We present only instructions that arise in compiling floating point programs with GCC. These are, for the most part, the scalar AVX instructions, although we document occasions where instructions intended for operating on entire data vectors arise. A more complete coverage of how to exploit SIMD capabilities of SZ and AVX is presented in WebAside opt SIMD on page 582, which we'll get to later. Readers may wish to refer to the AMD and Intel documentation for the individual instructions, which are 451. Is that page 451? No. Citation 451? Let's see if it's in the back of the book here. Yeah, here. 4 is AMD media instructions. And 51 is Intel's architecture software development manual. As with integer operations, note that the AT&T format we use in our presentation differs from the Intel format used in these documents. In particular, the instruction operands are listed in different order in these two versions. So here's our registers. These registers are used to hold floating point data. Each YMM register holds 32 bytes. The low order 16 bytes can be accessed as an XMM register. As is illustrated in figure 345, the AVX floating point architecture allows data to be stored in 16 YMM registers named 0 to 15. Each YMM register is 256 bits, 32 bytes long. When operating on scalar data, these registers only hold floating point data, and only the low order 32 bits or float or 16 bits for double are used. Assembly code refers to registers by their SC XMM register names XMM 0 to 15, where each XMM register is a low order 120 bits, 16 bytes of the corresponding MMM register. Okay, next page. So these are some instructions. So we got MOV instructions, VMOV, floating point movement instructions. These operations transfer values between memory and registers, as well as between pairs of registers. XMMM register, e.g. XMM3, M 32-bit memory range, and M 64-bit memory range. VMOV FD, move double precision to move aligned pack single precision. Aligned pack double precision. Okay. Floating point movement and conversion operations. Figure 3.46 shows a set of instructions for transferring floating point data between memory and XMM registers, as well as from XMM register to another without any conversions. Those that reference memory are scalar instructions, meaning they operate on individual rather than packed data values. The data are shown in the table as X. These instructions will work correctly regardless of the alignment of data. The code optimization guidelines recommend that 32-bit memory data satisfy a 4-byte alignment and that 64-bit data satisfy an 8-byte alignment. Memory references are specified in the same way as for the integer MOV instructions, with all the different possible combinations of displacement, base register, index register, and scaling factors. GC uses scalar movement operations only to transfer data from memory to an XMM register or from an XMM register to memory. For transferring data between two XMM registers, it uses one of two different instructions for copying the entire contents of one XMM register to another, namely VMOV APS for single precision and VMOV APD for double precision values. For these cases, whether the program copies the entire register or the low order value affects neither the program functionality nor the execution speed, and so these instructions, rather than the one specified to scalar data, makes no real difference. The letter A in these instructions name stands for aligned. When used to read and write memory, they will cause an exception if the address does not satisfy 16-byte alignment. A 16-byte alignment, okay. That was 8-byte. For transferring, I guess because it's the entire register is 32 bytes or 16-byte, yeah, okay. For transferring between two registers, there is no possibility of an incorrect alignment. As an example of the different floating point move operations, consider the C function. So we got float MOV. So it takes one float and a source and destination and returns a float. So this one says, hey, store source into V2, put V1 into destination, and return the source. So it does a read on the source and returns it, and does a read on its local register and writes it into destination. So two different types of MOVs. Is associated with the x86-64 assembly code. So we got our VMOV APS. So it says move, aligned, packed, single precision. And we do single precision because it's a float, not a double. These are all single precision operations. So we say, hey, go from XMM 0, which is the return value, and it's also the first arg. I like how simple the naming of the registers are. and the conventions around their use. It's very simple. It's like, okay, you got the first 8, the first half of them are the first 8 float arguments, and then the rest of them are all caller saved, general purpose. Okay, so we move that into 0 into 1. Why did we do that? Well, if we look at the code, I don't understand why we copy it into 1. Oh, because these other two values were RDI and RSI. Gotcha. So we just copy it so that we can have an appropriate return value. And we want v2, which is the read from the source, to go into the return value. So that's the next instruction. Dereference the pointer there and copy its value into there. And the last thing will be to take x of m1 and write it into RSI. Makes pretty clear sense there. Okay, we got a couple of tables up here. So we got 2 operand floating point conversion operations and 3 operand floating point conversion operations. So 2 operand, these convert floating point data to integers. And 3, these convert the data type of the first source to the data type of the destination. The second source value has no effect on the lower order bytes of the result. So one common theme that I'm seeing with these instructions is that they all start with V. VC, V, TT, SS, 2 SI. No, sorry. Convert with truncation, single precision to integer. CVT is probably convert. T is truncation. Single precision. Scalar. Single precision scalar. Or scalar single precision 2 scalar integer. We can see in this example the use of vmov APS instruction to copy data from one register to another, and the use of the vmov SS instruction to copy from memory to an XMM register and from an XMM register to memory. Figures 347 and 348 show sets of instructions for converting between floating point and integer data types, as well as between different floating point formats. These are all scalar instructions operating on individual data values. Those in figure 347 convert a floating point value read from either an XMM register or memory to write the result to a general purpose register. By converting floating point values to integers, they perform truncation, rounding values towards 0, as is required by C and most other programming languages. The instructions in figure 348 convert from integer to floating point. They use an unusual 3 operand format with 2 sources and a destination. The first operand is read from memory or from a general purpose register. For our purposes, we can ignore the second operand since its value only affects the upper bytes of the result. The destination must be an XMM register. In common usage, both the second source and the destination operand are identical as in the instruction so-and-so. This instruction reads a long integer from register REX, converts it to data type double, and stores the result in the lower bytes of XMM register XMM1. Finally, if converted between two different floating point formats, current versions of GCC generate code that requires separate documentation. Suppose the low order 4 bytes of XMM0 hold a single precision value. It would seem straightforward to use the instruction that to convert this to a double precision value and store the result in the lower 8 bytes of the XMM register XMM0. Instead, we find the following code generated by GCC. The von Pickelps instruction is normally used to interleave the values in two XMM registers and store them in a third. That is, for one source register contains words and another contains words so and so, then the value destination would be like that. Code above, we see the same register being used for all three operands. And so the original register held values x3 to x0, then the instruction will update the register to hold the values. The v convert ps to pd instruction expands the two low order single precision values in the source XMM register to be the two double precision values in the destination XMM register. Applying this to the result of the preceding on Pickelps von Pickelps instruction would give the value dx0 where dx0 is the result of converting x to double precision. That is, the net effect of the two instructions is to convert the original single precision value in the lower order 4 bytes of XMM0 to double precision and store two copies of it in XMM0. It's unclear why GC generates this code. There's neither benefit nor need to have the value duplicated within the XMM register. GC generates similar code for converting from double precision to single precision. Suppose these instructions start with register XMM0 holding two double precision values, then the vmov dedupe instruction will set it to x0x0. The v convert pd to psx instruction will convert these values to single precision, pack them into a low order half of the register, and set the upper half to 0, yielding a result so and so. Recall that floating point value 0 is represented by a bit pattern of all zeros. Again, there is no clear value in computing the conversion from one precision to another this way, rather than by using a single instruction. As an example of the different floating point conversion operations, consider the C function double f convert. So you got int I, a float fp, a double dp, a long lp. Float double long, int I double, okay. So this thing says, hey, the long pointer dereference is going to be stored into a long L. Just dereferencing everything locally. And then we convert the double into a long, the integer into a float, the long into a double, and return the float as a double. And its associated x86-64 assembly code. All the arguments for f convert are passed through the general purpose registers. Since they are either integers or pointers, the result is returned in register XMM0, as is documented in figure 345. This is a designated return register for float or double values. In this code, we see a number of the movement and conversion instructions of figure 346 to 348, as well as GCC's preferred method for converting from single to double precision. Practice problem. We're going to come back to these. So 3.50. I mean, I'll come back to them. I'm probably not going to do them, to be honest, unless they're super simple, because I just don't want to waste any more time on this stuff. All right. Let's go down here. Floating point code and procedures. With x86-64, the XMM registers are used for passing floating point arguments to functions and for returning floating point values from them. XMM registers used for passing floating point values. Yeah, you already talked about that. As is illustrated in figure 345, the following conversions are observed. Up to 8 floating point arguments can be passed in XMM registers. XMM 0 to 7, these registers are used in the order the arguments are listed. Additional floating point arguments can be passed on the stack. A function that returns floating point value does so in register XMM 0. A function that returns a floating point value does so in register XMM 0. All XMM registers are caller saved, and the callee may overwrite any of these registers without first saving it. When a function contains a combination of pointer, integer, and floating point arguments, the pointers and integers are passed in general purpose registers, while the floating point values are passed in XMM registers. This means that the mapping of arguments to registers depends on both their type and their ordering. Here are several examples. So you got double F1, int x, double y, long z. This function would have x as EDI or RDI, but EDI because it's an integer, XMM 0 as y, and z and RSI. Double F2, double y, int x, long z. This function would have the same register assignment as function F1. Yeah, because we just reorganized the arguments. We got them in order relative to the other arguments of that register type. Double F1, float x, double star y. So the first one, x, will be in XMM 0, and the other two will be RDI and RSI. Yep. Got another practice problem I'm going to skip. So that's 352. We'll come back to these, like I said. If they're easy, I'll do them. Okay. Floating point arithmetic operations. Figure 349 documents a set of scalar AVX2 floating point instructions that perform. Oh, I'm on the wrong page here. That perform arithmetic operations. Each has either one S1 or two S1 and S2 source operands and a destination operand D. The first source operand S1 can be either an XMM register or a memory location. The second source operand and the destination operand must be XMM registers. Each operation has an instruction for single precision and an instruction for double precision. The result is stored in destination register. Let me reread this. Each operation has an instruction for single precision and an instruction for double precision. The result is stored in destination register. As an example, consider the following floating point function. Say a function double float x, double b, int I. And we do this computation. The x86-64 code is as follows. And then we got a bunch of mathematical instructions for add, subtract, multiply, divide, maximum, minimum, floating point, square root. Scalar floating point arithmetic operations. These have either one or two source operands and a destination operand. The three floating point arguments A, X, and B are passed as XMM registers, while integer argument I is passed as register EDI. The standard two instruction sequence is used to convert argument X to a double. Another conversion instruction is required to convert an argument I to double. The function value is returned register XMM0. Okay. 3.53 and 3.54. What is all this stuff down here? Interesting. Defining and using floating point constants. Unlike integer arithmetic operations, AVX floating point operations cannot have immediate values as operands. I'll go ahead and highlight that. Instead, the compiler must allocate and initialize storage for any constant values. The code then reads the values from memory. This is illustrated by the following Celsius to Fahrenheit conversion function. Celsius to Fahrenheit double temp, return 1.8 times temp plus 3.20. Relevant parts of the x86 assembly code are as follows. So it's saying here, multiply XMM0 by LC2 plus the instruction pointer, and then add LC3 plus the instruction pointer to it and do ret. Because these are doubles, they'll have 64 bits. That must just be the assembler there. We see that the function reads the value 1.8 from memory location labeled dot LC2 and the value 32 from the memory location labeled LC3. Looking at the values associated with these labels, we say each is specified by a pair of .long declarations. The values given in decimal. How should these be interpreted as floating point values? Looking at the declaration labeled LC2, we see that the two values are decimal. Since the machine uses little endian byte ordering, the first value gives the low order 4 bytes. Yeah, that makes sense. While the second gives the high order 4 bytes. From the high order bytes, we can extract an exponent field 1023, for which we subtract the bias of 1023 to get the exponent of 0. Concatenating the fraction bits of the two values, we get a fraction field of so and so, which can be shown to be the fractional binary representation of 0.8. So it'll be 1 plus 0.8. Okay, these are binary bitwise operations, VX or VN. So all these instructions have V prefixes except for the square root. It's not a V square root, just a square root. And then we have 55. Using bitwise operations and floating point code, at times we find GCC generated code that performs bitwise operations and XMM registers to implement use of floating point results. Figure 350 shows some relevant instructions. Similar to their counterparts for operating on general purpose registers, these operations all act on packed data, meaning that they update the entire destination XML register, applying the bitwise operation to all of the data in the two source registers. Once again, our only interest for scalar data is the effect these instructions have on the low order 4 or 8 bytes of the destination. These operations are often simple and convenient ways to manipulate floating point values, as is explored in the following problem. So we got practice problem. Just skip over 356. Floating point comparison operations. AVX2 provides two instructions for comparing floating point values. So these have a U prefix, not a V. U compare ISS, ISD. These instructions are similar to the compare instructions in that they compare operands S1 and S2, but in the opposite order one might expect, and set the condition codes to indicate their relative values. As with compare quad word, they follow the AT&T format's convention of listing the operands in reverse order. Argument S2 must be an XMM register, while S1 can be either an XMM register or in memory. The floating point comparison instructions set three condition codes: the zero flag, the carry flag, and the parity flag. We do not document the parity flag in section 361 because it's not commonly found in GC generated x86 code. For integer operations, this flag is set when the most recent arithmetic or logical operation yielded a value where the least significant byte has even parity. For integer operations, this flag is set when the most recent arithmetic or logical operation yielded a value where the least significant byte has even parity, i.e., an even number of ones in the byte. For floating point comparisons, however, the flag is set when either operand is nan. By convention, any comparison in C is considered to fail when one of the arguments is nan, and this flag is used to detect such a condition. For example, even the comparison x is equal to x yields 0 when x is nan. The condition codes are set as follows. The unordered case occurs when either operand is nan. This can be detected with the parity flag. Commonly, the JP or jump on parity instruction is used to conditionally jump when a floating point comparison yields a unordered result. Except for this case, the values of the carry and zero flags are the same as those for an unsigned comparison. ZF is set when the two operands are equal. Oh, I'm on the totally wrong page here, I'm sorry. ZF is set when two operands are equal, and CF is some code here. Set when S2 is less than S1. Instructions such as JA and JB are used to conditionally jump on various combinations of these flags. As an example of floating point comparisons, the C function in figure 351A classifies arguments x according to its relation to 0, returning an enumerated type as a result. The enumerated types in C are encoded as integers, and so the possible function values are 0, 1, 2, or 3, which is negative, 0, positive, or other. Final outcome occurs when the value of x is nan, or probably infinity. I guess infinity would still have a 0, or yeah, maybe infinity doesn't fit in other. GCC generates a code shown in figure 351b for find range. The code is not very efficient. It compares x to 0 3 times. Even though the required information could be attained with a single comparison, it also generates floating point constant 0 twice, once using v XOR ps and once by reading the value from memory. Let us trace the flow of the function for 4 possible comparisons results. And then we go through and trace that. Let's look at the code first. Scattered enum, we got to find range. So we say, hey, if x is less than 0, it's negative. If x is equal to 0, it's 0. If x is greater than 0, it's positive. Or else we do other. Generate assembly code. So this is what we're going to step through. So x is less than 0, the JA branch in line 4. So we're taking in XMM0 and returning a range t, which is an enum, which is an integer, which would be on EAX probably. Yeah. All right. So the first instruction, we do XOR PS with itself, which sets it to 0, and then we say VU compare ISS, so comparing 0 with the x, and then we say, hey, if so this would be 0 minus x, jump above, which means that it wasn't zero minus x, jump above means that it was negative. Yeah, so it'll go to negative. And we do a comparison inverse to see if it's positive. But we say jump parity to say, hey, if that was a NaN, then go to other. L8. Go to post or NaN. Should be the other, right? And then other words, we move 1 into EAX, which is the return for 0. Strange. And then we say jump equal to L3, which is just the return if they're equal, which means that it's 0. And then this handles the NaN case. So we do another compare. This time we're doing it with between the first argument and LC0 RIP. So we're doing another compare against 0. This is where we're saying it's kind of like not efficient. And then we set result. Set BE. Not familiar with that instruction, but it's probably a conditional move operation type thing. Move ZBL. So that's a move 0 extended byte to long. So that puts the byte in there. And then we say add 2 to EAX. Which is either positive or other. And then we return. And this one just says, hey, you're negative. Okay. Okay. Homework problems 373 and 374. You're challenged to hand generate more efficient implementations of find range. X is less than 0, JA branch in line 4 we take in jumping to the end with a return value of 0. X is equal to 0, JA line 4 and JP branches will not be taken. With the JA branch, line 8 will, returning with EAX equal to 1. Yeah, we already covered all this when we read through the code. So now we got practice problem 57. There's lots of practice problems here, not a lot of reading. Okay. Okay, that's it. Observations about floating point code. We see that the generated style of machine code generated for operating on floating point data with AVX2 is similar to that what we're seeing for operating on integer data. Both use a collection of registers to hold and operate on values, and they use these registers for passing function arguments. Of course, there are many complexities in dealing with the different types and the rules for evaluating expressions containing a mixture of data types. And AVX2 code involves many more different instructions and formats than is usually seen with functions that perform only integer arithmetic. AVX2 also has the potential to make computations run faster by performing parallel operations on packed data. Compiler developers are working to automating the conversion of scalar code to parallel code, but currently the most reliable way to achieve higher performance through parallelism is to use the extensions to the C language supported by GCC for manipulating vectors of data. See WebAside optSimD on page 582 to see how this can be done. I will be doing that. 582, is that the same one that they called out before? There is another WebAside that he talked about earlier. Well, I'll highlight it here. Yeah, it's the same one. We'll get to that soon. All right, summary. In this chapter, we have peered beneath the layer of abstraction provided by the C language to get a view of the machine-level programming. By having the compiler generate the assembly code representation of the machine-level program, we gain insights into both the compiler and its optimization capabilities, along with the machine, its data types, and its instruction set. In Chapter 5, we will see that knowing the characteristics of a compiler can help when trying to write programs that have efficient mappings onto the machine. We have also gotten a more complete picture of how the program stores data in different memory regions. In Chapter 12, we will see many examples where application programmers need to know whether a program variable is on the runtime stack. Let's reverse back, I wasn't paying attention. In Chapter 5, we will see that knowing the characteristics of the compiler can help when trying to write programs that have efficient mappings onto the machine. We have also gotten a more complete picture of how the program stores data in different memory regions. In Chapter 12, we will see many examples of where application programmers need to know whether a program variable is on the runtime stack, is some dynamically allocated data structure, or part of a global program data. Understanding how programs map onto machines makes it easier to understand the differences between these kinds of storage. Machine-level programs and their representations by assembly code differ in many ways from C programs. There is minimal distinction between different data types. The program is expressed as a sequence of instructions, each of which performs a single operation. Parts of the program state, such as registers and the runtime stack, are directly visible to the programmer. Only low-level operations are provided to support data manipulation and program control. The compiler must use multiple instructions to generate and operate on different data structures and to implement control constructs such as conditionals, loops, and procedures. We have covered many different aspects of C and how it gets compiled. We have seen that the lack of bounds checking in C makes many programs prone to buffer overflows. This has made many systems vulnerable to attacks by malicious intruders, although recent safeguards provided by the runtime system and the compiler help make programs more secure. We have only examined the mapping of C onto x86-64, but much of what we have covered is handled in a similar way for combinations of language and machine. For example, compiling C++ is very similar to compiling C. In fact, early implementation of C++ first produced the source-to-source conversion from C++ to C and generated object code by running a C compiler on the result. C++ objects are represented by structures similar to a C struct. Methods are represented by pointing to the code implementing the methods. Methods are represented by pointers to code implementing the methods. By contrast, Java is implemented in an entirely different fashion. The object code of Java is a special binary representation known as Java bytecode. This code can be viewed as a machine-level program for a virtual machine. As its name suggests, the machine is not implemented directly in hardware. Instead, software interpreters process the bytecode, simulating the behavior of the virtual machine. Alternatively, an approach known as just-in-time compilation dynamically translates bytecode sequences into machine instructions. This approach provides faster execution when code is executed multiple times, such as in a loop. The advantage of using bytecode as a low-level representation of programs is that the same code can be executed on many different machines, whereas machine code we have considered runs only on x86 64 machines. Bibliography notes and homework problems. All right, well, that's the whole floating point section. Let's go back to 350. So that's here. For the following C code, the expression val1 minus val4, sorry, I need to go back here. Actually, I want to read the biographical notes. Sounds weird, but both Intel and AMD provide extensive documentation on their processors. This includes general descriptions of an assembly language programmer's view of the hardware, as well as detailed references about the individual instructions. So that's 250 and 351. Reading the instruction descriptions is complicated by the facts that all documentation is based on Intel assembly code format. There are many variations for each instruction due to the different addressing and extension modes. Addressing and execution modes. And 3, there are no illustrative examples. Still, these remain the authoritative references about the behavior of each instruction. The organization x86 64 org has been responsible for defining the application binary interface for x86 64 code running on Linux systems. This interface describes details for procedure linkage, binary code files, and a number of other features that are required for machine code programs to execute properly. Let's check that out. It just goes to AMD. That's kind of bullshit. Yeah, that's where it started redirecting. So it must have been 2016 when they wrote the frickin' book that they stopped doing this. I've never seen that before, where a website just goes offline like that. Oh. Alright. Not super helpful. Very dated. Alright, well, let's try doing it one more time. Maybe they got like a different scrape or something that succeeded. Seems like it's like none of these scripts are gonna work here. 96 captures. Are any of them good? There's just a freaking header here. Okay. Oh, here we go. abi.pdf. And that's not available in the newer scrapes. Oh, it was, but it didn't load. Okay. How long is this? 127 pages. That's funny. I wonder if that was intentional. Let's continue reading this. Organization x8664.org has been responsible for defining the application binary interface for x86 code running Linux systems. If we go to 77 reference, is that even in here? Yep, that's exactly what we're looking at. As we have discussed, the AT&T format used by GC is very different from the Intel format used by Intel documentation and by other compilers, including Microsoft compilers. Muchnick's book on compiler design is considered the most comprehensive reference on code optimization techniques. It covers many of the techniques we discussed here, such as register use conventions. Register uses conventions. Much has been written about the use of buffer overflow to attack systems over the internet. Detailed analysis of the 1988 internet worm have been published by Spafford, as well as by members of the team at MIT who helped stop its spread. Since then, a number of papers and projects have generated ways both to create and prevent buffer overflow attacks. Seacourt's book provides a wealth of information about buffer overflow and other attacks on code generated by C compilers. Let's check out the Muchnick's compiler design book. Kind of interested in that, since I'm kind of getting into compilers later this year. Alright, what do we got? 80 here. Advanced compiler design and implementation. '97. Okay. What was the other reference I was looking at here? '97. Secure coding in C and C++. I've heard of this before. Is this actually downloading the PDF? Good job, Google. Just feed me up a bunch of piracy. Isn't there a second edition? Yeah. Still has it 2013 when that was published. 13 years ago. I'm getting fucking old, man. Oh, since it downloaded it for me. Oh, it's like a shitty PDF. I hate these things. I'd rather just look at the sample here. I hate it when things are not properly typeset. Okay. Running with scissors. I gotta send that to a friend. That's so funny. Okay. Enough goofing about. Let's go back and do our problems. Our floating point problems. Get out of floating point hell here. Close that out. What is all this stuff? I didn't do that, did I? Amazon. Alright. So let's go back to this problem. Let's practice problem 3.50. It's the first compilation disassembly. Oh no, it's a separate one. For the following C code, and I'll go back to the actual page over here, which was here, 350. For the following C code, the expression val1 minus val4, val1 through val4 all map to the program values I, F, D, and L. Determine the mapping based on the following x86-64 code for the function. Was it determine the mapping based on the phone? What mapping? What are you talking about? For the following C code, okay, the expression val1 No? The expressions val1 through val4 all map to the program values. Oh. Okay, I got you. You're saying which ones are which. Because this is a lie. There are no val1 through val4. Okay. So val1, 2, 3, and 4. And we'll just do one of these deals here. Okay, let's read through here. Well, val 4 is easy because that's going to be XMM0 coming out of the return here. So that's dereferencing RSI. RSI is FP. So that'd be F. Val 4 is going to be F. Then what else we got going on here? We got some other deals here. Let's try to find the end pointer. So we're going into EAX and R8D. So those are two additional dereferences. So that's going to correspond to the double and IP dereferences. So our DI is IP dereference. This is going to be I. And then RDX is going to be DP. So it's going to be D. And where does EAX? It's being used with XMM1. RD8, which D goes into RDI dereference. RDI dereference is of course IP. So saying IP is going to be the int from DX. RDI is going to be I here. So that's this line here, and that's saying that R8D is coming from RDX, which is D, which is DP. So basically D is going to be val 1. That's another easy one, D. So it takes care of that one. RSI, XMM1, EAX. So we got single and double. Okay, so that's in order. So here we're taking EAX into XMM1 and then taking XMM1 into RSI. Dereferenced. RSI dereference. It's going to be FP. definitely going to be that. XMM EAX. EAX got I stored in it. So I basically gets converted into a float and stored in float pointer. That would be where I so I would be the next one, and then just looking at the next one, I don't even have to look at it because it's the only one left, but I'll look at it anyways, which is RCX is going to RDX, and DX of course is DP. Yep. RCX is RL, so it's going to be L. So DILF, DILF. Okay, 350. This exercise requires you to step through code, paying careful attention to which conversions and data movement instructions are used. You can see that the value is being retrieved and conventions as follows. Value DP is retrieved and converted to int line 4 and then stored at IP. We can therefore value D. Val 1 is D. DILF. Yeah, I don't need to read the whole thing. Okay, got that one. Let's go to 51. The following C function converts an argument of type source T to a return value of type destination T, where these two types are defined using a type def. So you say, hey, source T cast into dest T, and you get returned. Doesn't even need the temporary variable. For executing on x86-64, assume that argument x is either in XMM0 or in the appropriately named portion of the register RDI. One or two instructions are to be used to perform the type of conversion and to copy the value to the appropriately named position of the register REX integer result. So you know destination is an integer type. Or XMM0 floating point. Oh, no, we don't know that. Okay. Show the instructions including the source and destination registers. It's going to be hard because I didn't really pay attention, but there is a table that I can reference. So let's go to GitHub, Markdown table generator. And there is 1, 2, 3, 4, 5, 6 by 3. 6 by 3. Create. It's going to be TX, TY, and instructions. Long to double. OU. VCT, VT, SI2 SDQ, RDI to XMM0. And then we want to do double to int, double to float, a long to float, and a float to long. You know, he doesn't say anywhere here that I can't use a compiler to do these things. It'd be good practice for me to do that anyways, right? Why don't we do that? Vim test 3 underscore, what is this, 51? .c main. I don't think I need a main. What I do need is close this out. CVT of X, and it's going to be a return of that type to X. Yeah. So in here, he gives the example of converting a long to a double. So we say convert L to D. And then this would be double to int, double to the integer. This will be convert double to a float. This will be convert long to a float. That's fine. Oops. And then this will be convert float to long. So double int float float long, double int float float long. And this will be long double, sorry, double int float float long, double, wait a minute, what? Double int float float long, long double double long float. Yep, okay. And this needs to be renamed convert float to long. There we go. And I'm gonna make some predictions here. So for this one, the long to a double, there needs to be a convert, actually, let's just go ahead and do our make file here. We'll say here, since we're converting, creating object code. This would be what, 51? 51, oh, no, we want to do it like this. 51, oh. 51 test3 51.c. Oh, we'll just do it like this. As we test 51.c, and we're gonna do our GCC, I guess. What's the default here? I guess we use Zig for default. And for .os, we do it like this. That's for .s. Clang.o. I got so many things here. OG, G, C. There we go. And then up here, I gotta add my target, which is build test 3 51.0. Make. Okay. Readelf, disassemble, build test 3 51.0. What is it? Disassemble symbols. Where's the disassembler? Huh? That's a little bit too much. So it's going to be a bunch of shit. So instead of doing that, we're going to go back here and say, hey, I just want a specific symbol. Display assembler contents of executable section of all sections. Okay, maybe just do lowercase d. Hey, look at that. Gave us what you wanted. Okay. And we'll just copy these and we go into our problems. And long to double. So that's just preamble, saving off that, storing the RSP, giving us some stack space, and then we pop and return. So RDI, because I guess you can't use a register there. V, this is just RDI, XMM. Yeah, okay. Okay, so in here is the double to int. So we're going to vmove this into stack, and then we're going to use it again. I think we can just use registers for both the operands here. I think it's only memory can't be the same. So that will go there. Convert double to float. So again, why? So he's saying move XMM into the stack, move the stack into XMM1. We're not doing anything special here. So I'm just saying XMM0. I think that'll work. I mean, fuck remembering these names, man. Like, it's not even worth the effort at all. Let's double the float. This is moving RDI into there, so we can replace this with RDI. And I think there's a single, or yeah, I think this is the better form here. And then finally, same thing. Okay. Let's go and see what they said here. 51. Use case can't be handled by selecting the appropriate entries from tables in figure 34748 or using one of the code sequences for converting between floating point formats. So VCVTT SD2SI XMM0 EAX, got that one. V unpack LPD. float to double. Wait a minute. I don't have a float to double. What's going on here? That was wrong. Wrong to float. VCVTS I2SQ RDI XMM0. Yeah. And then float to long is VCVTTSS 2SIQ. The Q is optional. XMM0 RAX. Yeah. All right. Next problem, 52. For each of the following function declarations, determine the register arguments. Determine the register or assignments for the arguments. A, B, C, and D. That should be pretty easy. I'll do that one. I saw this one when I was going through the chapter, and I was like, I kind of want to stop to do this one. But I also didn't want to. I kind of like reading the chapter first, or at least a good section, even though the authors don't recommend it. The authors don't also fuck up on all the answers to the problems, so I'm not like too crazy about them. All right, so we got double G1, double A. So they want register do they want the returns too? So the first one will be XMM0. Long will be, I have to reference my other table in this one. I think it's long, so that'd be 64 bits. RDI. A float, which is 32 bits. XMM. I need to put a little sticker in this thing here. Grab my little stickers here. These have been handy, but they're not too durable. Like the paint just like rips off of them. Okay, so YMM. XMM's 128-bit. So it would just be MM? I don't know. Good question. XMM1 and int D, which is 32 bits. This would be the second, which is RSI, I think. Yeah, RSI, it's 32 bits, it's ESI. ESI. So it might be, and then the ret will be 0. Alright, let's look at the answers for this first one. The basic rules for mapping arguments to registers are fairly simple, although they become much more complex with more and other types of arguments. Registers A, XMM0, RDI, XMM1, and ESI. And the ret. Okay, they don't care about the ret. So I got that right, at least. So next one is A is an int, so it'd be EDI. Int pointer, which would be RSI. Another pointer and a long. RDX, RCX. So that's B, EBI, sorry, EDI, RSI, RDX, RCX. Yep. And then C is another one here, pointer, which would be RDI. Double, which would be XMM0, int, which would be ESI, and then float, which would be XMM1. RDI 0, ESI 1. Yep. And then D is float, which is XMM0. Int star, which is a pointer, which would be RDI. Float C, which would be XMM1, and then double D, XMM2. 0, RDI 1, 2. Yep. Okay, next problem. 53. For the following C function, the types of, let me go over here. For the following C function, the types of the 4 arguments are defined by typedef. When compiled, GC generates the following code. Determine the possible combination of types of the 4 arguments. There may be more than one. I'm going to skip that one. Don't really care about it. Skip. Seems like busy work. For func2 has the following prototype. GC generates the following code. Write a C version of func2. Skip. 55. Show the numbers declared in label LC3 and code the number 32. Skip. Uh, 56. Consider the following C function where xbur is a macro defined upon define. So it's a call. So you say simple func, double, call it below. We show the AVX2 code generated for different definitions of xbur, where value x is held in XMM0. All of them correspond to some useful operation on floating point values. Identify the operation, what the operations are. Your answers will require you to understand the bit patterns of the constant words being retrieved from memory. I can do this one. All right, we're on 56 now. Function func3 has the following prototype. For this function, GC generates the following code. Where's C version? I'm gonna skip that. Okay, that's chapter 3 then. We are now on to processor architecture. Not doing any of the homework problems. Chapter 3 is done. Okay, processor architecture. This is where we get to the fake architecture thing. Let's check where we're at with lectures. So GitHub. Processor architecture. We have the TAC lab and stacks. We could probably do that. What's today? Today's Tuesday already? God damn. Okay. Yeah, doing the TAC lab might be something we do. Program optimization. I feel like I want to come back to the attack lab when I have a day just to do it. Like I'll start on it. Like tomorrow would be nice. Wednesday I have the entire day to do it. Start on it early in the morning and just focus on it the entire day. There were these asides that I skipped over. ASM I32 and EASM. Let me see if I want to skip those. CSAPP, webasides. So this one is how many pages? About 20 pages. It's 386 programming. How many problems are there in this thing? I don't like it when he puts problems. Oh fuck, he put problems in here. It's like an aside should just be an aside that you read about and you're like, oh, that's nice. And then move on with your life. I might just read it and not do the problems. Let's go ahead and read it. Starting with the introduction to Intel 386 processor, 1985 processor. Let me move this thing back so I can read a little bit clearly here. Okay, starting with the introduction of the Intel 386. In 1985, processors in the x86 family had been able to execute 32-bit programs in machine language known as IA32 or Intel architecture 32 bits. With these programs, all pointers are 32 bits long, and hence the addressable range of the code and data in program is 4 gigabytes. CSAPP 3E, Chapter 3, describes x86-64 machine language, the 64-bit extension to IA32 introduced by AMD in 2000. So long ago, damn. First implemented in their Opteron processor in 2003 and adopted by Intel with the Pentium 4E in 2004. Even though most x86 processor manufacturers today are designed to execute x86-64 programs, they can also execute IA32 programs in a compatibility mode. Both IA32 and x86-64 programs can coexist on a single machine. GCC will generate IA32 code when given command line option -M32, and it will generate x86-64 code when given the command line option M64. Many application programs are still compiled for IA32 since most programs require far less than 4 gigabytes of memory, and the 32-bit pointers make IA32 data structures more compact. In this document, we described IA32 programs based on the assumption that you, the reader, are already familiar with x86-64, although this reverses the order in which these two machine languages were devised. So we got different set of registers here. Well, it's the same naming, but EAX, ECX, EDX, EBX, ESI, EDI, ESP, EBP. You'll find that having a background in x86-64 makes understanding IA32 fairly straightforward. This document does not provide a comprehensive coverage of all aspects of IA32, but rather those features that are most prevalent in machine language programs generated by GCC. The authoritative reference for IA32 is the documentation provided by Intel registers. Figure 1 illustrates a set of 8 general purpose registers used to hold both integer and data and pointers. You see that several aspects, these registers are subsets of those available in x86-64 program. There are only 8 registers instead of 16. The maximum register size is 32 bits. The lower order registered bytes are only directly accessible for the first 4 registers. There are many similarities between how registers are used in IA32 and x86-64. Both has a designated register to save this as a stack pointer, ESP. This register should only be altered in accordance with the stack discipline used by programs. Both have designated register that can optionally serve as a frame pointer, EBP. We will describe the use of frame pointers as part of our discussion of procedures in Section 4. Both use a designated register, EAX, for IA32 and RAX for x86-64 for returning pointer or integer values from procedures. With Linux, some registers are used according to caller save stack discipline, while others follow a call save discipline. So we got instructions, procedures, some diagrams. As one would expect, IA32 assembly has the same overall form as does x86-64, but for the most part, the instructions are a super subset of those available in x86-64. In particular, the Q variants of data movement and arithmetic instructions are not available, but the other versions are. So, for example, programs can use instruction move L to move a double word, move W to move word, move B to move byte, but not move Q, move quad word. For instruction arguments that reference memory locations, the base and index registers must be one of the 8 double word registers shown in Figure 1. Thus, typical memory referencing instructions use move EAX into 8 ESP, add 1 to, yeah, okay. IA32 has several instructions that are not allowed in x86-64, as well as others that have slightly different effects due to the convention that addresses are 4 bytes rather than 8 bytes. Other differences for these instructions are, of course, are that the stack pointer rather than so-and-so and the frame pointer used and modified by the leave instruction is EBP rather than RBP. Rather than LAAQ, the load effective address is called LAL. The destination must be one of the double word registers of Figure 1. The push instruction is called push or push L, and the pop instruction is called pop or pop L. They just decrement and increment stack pointer by 4 respectively. Procedure calls and returns use a call and ret instruction, but these are decrement and increment the stack pointer by 4. The leave instruction operates on registers ESP and EBP. It has no arguments and is equivalent to IA32 instruction sequence. Move the EBP into ESP and pop the EBP. It is used in procedures that make use of the frame pointer as described in subsection 4.1. Special arithmetic operations. These operations provide full 64-bit multiplication and division. Rows signed and unsigned numbers. The pair of registers EDX and EAX are viewed as forming a single 64-bit quad word. Interesting. Figure 2 shows the IA32 instruction for arithmetic operations that involve 64-bit quantities. These include signed and unsigned multiplication instructions that compute the full 64-bit product of two 32-bit numbers. They also include signed and unsigned division, where the dividend is 64 bits. In both cases, 64-bit quantity is held in registers EDX and EAX. Instruction CTLD provides a way to extend the signed bit of EAX into EDX. Note the similarities to the x86-64 instruction that involve 128-bit quantities, which is in Figure 312. I don't know where the fuck Figure 312 is though, but maybe we go back here. This was Figure 3.2. This was Figure 318. Means maybe here. 310. 311. 312. Okay, yeah. IA32 procedures. Perhaps the most striking difference between IA32 and x86-64 concerns The structure of procedure calls. Most significantly, IA32 requires all arguments to be passed on the stack, whereas x86 requires use of the stack for arguments passing only requires use of the stack for argument passing only if there are more than 6 arguments. As we saw in CSAPP 3E, Chapter 3, many x86 procedures do not require passing arguments on the stack. And indeed, they often use the stack only for saving the return pointer. IA32 programs also require greater use of the stack to hold local variables due to the small number of registers. We split our presentation of IA32 procedures into 2 forms, depending on whether or not the code makes use of the frame pointer. Traditionally, all IA32 code use frame pointers, and so we refer to this approach as classic IA32. More recent versions of GCC generate IA32 code that does not use frame pointers, and so we refer to this approach as modern IA32. Whichever approach is the default for a particular compiler, it's possible to force the other convention using the command line argument f omit frame pointer or f no omit frame pointer. Code using frame pointers can be freely mixed with code that does not, as long as EBP follows a call save convention. That is, the function that modifies EBP must restore it to its former value before returning. In addition to presenting general concepts, we will demonstrate how procedures are implemented in IA32 using the 2C functions defined in Figure 3. The functions both have 2 arguments, but they differ slightly in the argument types. Function call fun has both arguments of type int as given by the following prototype: call fun x and y. And then fun is just called by x, or called by call fun, and it's given x and a pointer to y. And it just does the addition of the dereferencing. Interesting. Function fun, on the other hand, has one argument type int and another type int star. Both functions return values of type int as a result. Classic IA32 using frame pointers. The concept of a frame pointer is to have a designated register holding the address of the beginning of the stack frame for the currently executing function, with the stack pointer indicating the end of the stack. These 2 registers bracket the stack frame. Figure 4 shows the overall organization of IA32 runtime stack, illustrating the case where the procedure P is called by procedure Q. This figure uses the same conventions as we shown for the x86 runtime stack. In particular, both x86 and IA32 frames grow towards lower addresses. We draw our stack with the address increasing from bottom to top. This has the particular effect of that the stack's top is shown at the bottom of the diagram. Yeah, so we have the same EBP, which points to up here. So the value stored here points to up here, and this thing, EBP, just points there. And you have saved registers, local variables. Your addressing is relative to EBP instead of ESP, although some things are relative to ESP. For the argument build area, if we're referencing like the return address or arguments from the previous function, you have to do those off of EBP. Basically, EBP is needed for, in its traditional use, is needed for referencing values in the caller's frame, such as arguments that are passed to the function when the function has a variable sized frame. Otherwise, EBP can be repurposed as a general purpose register. And I can see why that would be useful in 32-bit code, but I just don't see I don't buy, like ChatGPT was saying 2 to 5% performance improvement on AMD 64, and I just don't buy it. Like, That doesn't make sense to me. AMD64 has plethora of registers. Like you're not pressured for registers as much as you are with x86 32-bit. So I don't know. All right, let's continue reading. In this figure, register EBP indicates the beginning of the stack frame for Q. By convention, the previous value EBP, in this case, the 1 for procedure P, is stored on the stack at the position indicated by EBP. Having this value on the stack enables it to be restored as the current procedure returns. Before calling Q, procedure P stores the argument on the stack frame. These are retrieved within Q with memory references that use the appropriate offset from register EBP. Such references are indicated in figure 4 by the notation EBP plus K. Within the stack frame Q, there may be space for save registers, local variables, and to store the argument values for any procedure to be called by Q. Typical IA32 procedures save and restore registers using the push L and pop L instructions, and they allocate additional stack space by explicitly decrementing the stack pointer. Local variables are typically accessed with memory references having offsets to the frame pointer, indicated by the figure by the notation EBP minus K. And newly generated argument values are written with memory references having offsets from the stack pointer, indicated by the figure ESP plus K. We can see how IA32 programs make use of the stack and frame pointers by studying the assembly code for a function called fun, as is shown in figure 5a. Figure 6 diagrams the state of the stack at 2 points in execution of this function. So we got disassembly and we got our stuff here. So call fun. We push our EBP onto the stack. We set our EBP to our ESP. We then increment or decrement our ESP. We can then say, hey, add 12 to the base pointer and store it in EAX. Store the address in EAX. And then we're going to move that pointer value to ESP plus 4. So that's like an argument. And then we move EBP plus 8, which is the previous caller. So it's the argument for Y probably. Or X, sorry. X. And we move that to EAX, and then we move EAX into ESP, so we store X, since this is like a move instead of LEA. We're actually copying the X value, and then call fun, and then we leave in ret. And then fun does something similar, where it pushes its EBP onto the stack, moves its stack pointer to be EBP, decrements its stack pointer. Wait a minute. It doesn't decrement its stack pointer because it doesn't need any stack space. Normally it would, but there's no stack space needed here. So it grabs the argument for EBP and stores in EAX, dereferences the Y value, dereference it and stores in EAX, and then adds the value passed in A to EAX. And then we pop EBP and return. So EAX is already set, so that comes back up here. And it gets passed all the way back up the stack. Okay. Since we didn't use any stack space, we didn't have to leave. That's why. And leave is just doing a pop and restoring the stack pointer. Okay. Boom, 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 boom. Upon entry to this, I don't need to read all this. I already read the disassembly. Alright, we'll read it anyways. Power read it. Upon entry, the state of the stack is illustrated in Figure 6a. The call instruction has just pushed the return address onto the stack prior to the function that called call fun puts values of arguments y and x onto the stack. Each of the three topmost stack elements, the return address, x, and y, are 4 bytes long. Note also the ordering of the arguments of stack. Those are the earlier in the list. The procedure parameters are closer to the top of the stack. The first three instructions call fun, set up the stack frame to construct a structure illustrated in Figure 6b. The first instruction saves the current value of EBP on the stack, and the second updates EBP to point to this position. This combination establishes the convention for frame pointer illustrated in Figure 4. The third instruction decrements the stack pointer by 8, allocating enough space on the stack to hold two 4-byte arguments for function fun. At this point, we can see that arguments x and y are stored at the stack at offset 8 and 12 from EBP. Respectively, the arguments A and BP for fun should be stored on the stack at offset 0 and 4 from ESP, respectively. These conventions follow the illustrated in Figure 4 for accessing arguments called fun, blah, blah, blah. Suffice to say here that when fun, the stack will still have the same structure as is illustrated in, okay. Okay, none of this is important. Push L instructions used to push the value of the frame pointer on the stack. Move L instructions used to copy the stack pointer to the frame pointer. Establishing the frame pointer for this procedure. If any call E saved registers need to be saved, these are pushed on the stack via push L instructions. Neither of the examples require this. If any space needs to be allocated for local variables or for argument build area, the stack pointer is decremented by the appropriate amount. Whew. More recent versions of GCC generate IA32 code without frame pointers, which looks like this diagram. We just have a stack pointer, everything's referenced off of that. No RBP stored, no leave instruction. Unless you're using it, because it's call E saved. Okay. Well, that was interesting. Combining assembly with code with C code. Okay. How many pages is this? This is less than the other one. 15. I think what I'll do is I'll mark that as red. We need to go out of here. So we're not in chapter 3 anymore. All right. Let's go ahead and get the lecture loaded up for here. We'll go ahead and watch that, which is program optimization.
We've now gotten through all the lectures on machine code, and we're starting to talk about, okay, now that you know this stuff, what can you do with it? Is along the lines of that. This is sort of what you are now empowered to do now that you can look at and understand machine code. This material is a little, there's a whole chapter of the book, chapter 5, on performance optimization, and we're only going to do one lecture on it. And we don't have any labs, unfortunately, that really get you to push your limits on this, which is too bad because it's a very interesting topic. And
all right, let me rewind this.
So we've now gotten through all the lectures on machine code, and we're starting to talk about, okay, now that you know this stuff, what can you do with it? And this lecture is along the lines of that. This is sort of what you are now empowered to do now that you can look at and understand machine code. This material is a little, there's a whole chapter of the book, chapter 5, on performance optimization, and we're only going to do one lecture on it. And we don't have any labs, unfortunately, that really get you to push your limits on this, which is too bad because it's a very interesting topic and one I think you'd find yourself well equipped for. There are typically a few small exam problems that are sort of based on some of the material here you'll find in old exams. But really the idea is, how can I make programs run fast? Given that I've sort of algorithm I'm using, and
why did they go into program optimization memory hierarchy? So they just spent like a shitload of time on all that machine level stuff, and then they're just gonna skip over processor architecture? And to go straight into optimizing program. They skip a whole chapter in the lectures. Jump into optimizing, it's a whole chapter, and then memory hierarchy. Okay, well, I'm gonna skip it too then. They skipped it.
In a program that runs, how can I make it run faster? And one of the themes of it is you can sort of do this in layers. You can sort of, first of all, do the stuff to avoid sort of things that make programs run slow across a wide variety of machines. And just make your, I would describe it as making your code more compiler friendly, and we'll talk about what that means. And you have to have some understanding and appreciation for what compilers are good at and what they're not good at to be able to do that. And I describe these as the kind of things that you should just be in the habit of when you write programs, writing this code that I'll describe as compiler friendly. And then the next level is, okay, given that I've sort of taken away the things that really shouldn't have been there in the first place, now how can I make my programs run faster? In particular, how can I adapt it to the capabilities of the types of machines that this program is going to run on? And that can, again, go from ones that will generally make programs run fast across a wide variety of machines to ones that become very specific. And very specific is a risky thing, because even in the world of, say, x86 machines, there's quite a variety of them that are available at any given point in time, and they evolve over time as well. So you can make programs run really fast on one particular model of one x86 processor, but it might not, that if you're trying too hard, you'll find your effort is sort of wasted when you move it to another. On the other hand, these general ideas I'm going to describe actually work across quite a range of machines. So, and I'll talk about that more as we go along. So, it used to be in the bad old days that if you wanted a program to run fast, you had to write it in assembly code. And that's just plain not true anymore. And if anyone tells you it's true, it's because they're full of it. It's just not true. Except for the exceptional case where you're running on a very small resource-constrained machine, such as a very small underpowered embedded system. So let's just assume that we're going to use a compiler, and we'll assume for this course we're going to use GCC because it's generally available. It's not actually the best compiler out there. Intel makes a compiler that costs money to license and stuff, but it really can do some amazing things. And other compilers exist, but GCC is sort of a good enough compiler for most people. But there's some features of some things that sort of puzzle compilers that they don't really understand. Compilers don't really understand, for example, that the numbers you're using when you say it's an int might actually range over a much smaller set of values. And they have a very hard time understanding memory referencing patterns and the effect of procedure calls. And so in general, what happens with the compiler is it has a whole sort of cookbook of optimization strategies and some recipes for how to try out different compiler in some things, but GCC is sort of a good enough
must not operate under fundamental constraint, must not cause any change in program behavior except possibly when program making use of non-standard language features, often prevents it from making optimization that would only affect behavior under pathological conditions. So like undefined behavior. Behavior that may be obvious to the program can be obfuscated by languages and coding styles. Data ranges may be more limited than variable types suggest. Most analysis is performed only with procedures. Whole program analysis is too expensive in most cases. Newer versions of GC do not implement analysis within individual files, but not between. New versions of GC do interprocedural analysis within individual files, but do not between code and different files. Most analysis is based only on static information. Compiler has difficulty anticipating runtime inputs. When in doubt, compiler must be conservative.
Cookbook optimization strategies and some recipes for how to try out different strategies and apply them. But in general, if it ever feels like this code is something that it doesn't feel confident about being able to make certain transformations, then it just won't. It will keep things sort of a more direct implementation of exactly what you describe. And we'll show examples of that as we go along. So the thing about optimizing compilers, it always has a fallback position, which is to not optimize. And sometimes that will get in trouble if you want your program to run faster and the compiler just, in its own conservative way, decides not to do that optimization. And one of the tricks that you'll find is pretty useful now that you can read assembly code is you run the compiler, you see what optimizations it does, and if it doesn't make something that you expect it to be able to do, you go back and figure it out. So it's very common, by the way, to rewrite your in the same language and sort of tune it and up to make it run faster, to make it more compiler friendly. There's nothing wrong with that, as long as you don't then just totally obliterate the program and make it totally illegible. So let's just describe some sort of general optimizations. And you've actually seen versions of this in some of the assembly code we've already looked at. And I'll use mostly sort of examples from multi-dimensional arrays because those are actually fairly easy optimization type of tasks. But these apply to other types of program as well.
Optimizations that you or the compiler should do regardless of processor, compiler, code motion, reduce frequency with which computation performed, if it will always produce the same result, especially moving code out of a loop. Yeah, instead of doing n times I inside the loop, you can just move it outside the loop.
You saw before when we described how to do array indexing in multidimensional arrays that the old style of code was if you had a variable size array, it was up to you, the programmer, to write the formula of how you convert row I, column j into a position in a one-dimensional array. So remember, it's just the number of columns times the row number plus the column number is the standard one. So that would give, this would be pretty typical code then. It would give you a notation like this. If you wanted to set one row in array A to the values in a one-dimensional row B, this is the code you'd write. And the main observation is within this loop, the only variable that's changing is j. And so from the array perspective, this computation n times I, if it gets repeated over and over again within this loop, then you're just wasting, it's a wasted effort. So you can do what's called code motion, which is to pre-compute the value of n times I outside of the loop, and then use it over and over again inside. And compilers will generally do this when they can detect, for example, that it's a array access code and it has this technique. It will generally do optimizations like this if you set, say, an optimization level of 1 or higher to GCC.
Compiler generated code motion 01, so that pulls it out. Yep.
We can see this, in fact. This is this code, and I ran it through GCC using optimization 1. And you see, as this red instruction shows, it boosted this multiplication outside of the loop. And it's a little as if you, actually, this code does even more. It turns the code into something that looks more like a pointer code, accessing array A, and stepping through that element by element of the array. Another one, and we've seen this already, that when GCC turns a multiplication or a division by shifting and adding and operations like that, multiplication or division by constants, we've seen examples of that. And a similar one would happen if we took that program I showed before and applied it to every row. So we wanted to set for array A, we wanted to set every one of its rows to the value of the one-dimensional array B. Then again, if we took that code, we boosted the n times I in there. So now the inner loop is good, but you realize that this multiplication isn't necessary either, because what we're doing from I equals 0 to I equals 1 to I equals 2 is we're just increasing the parameter ni by, we're adding n to it. So we can, and that's called a reduction in strength. We've taken a multiplication and turned it into addition because there's some predictable pattern of how this variable ni is going to be updated. Another example, and again, array indexing is a good example for optimizations. Imagine we had an image that we represent as a two-dimensional array of pixel values. And we want to do something that's a filtering operation where we want to take the sum of the 4 neighbors of a given pixel, north, south, east, and west, and average those together, or sum them together. And so the natural way you'd write this in C is to say I want usually in images you count from the top down, and so you'd say this is the pixel above, this is the pixel below, this is the pixel to the left, and this is the pixel to the right. And if you do this and just compile it straight through, unfortunately, it appears as if there's 3 different multiplications by n, I minus 1, I plus 1, and I. And if the compiler isn't too clever, it won't realize that these are related to each other, and it will issue 3 different multiply operations just to do this 1 pixel thing. Whereas if I'm a little more clever, and this is one where I manually rewrote the code so that the compiler would pick it up, I'd say, well, if so ij is I times n plus j, and I can get the pixel above the pixel below by shifting that, offsetting that by a value of n. And then it will issue the code. This will compile with the code with just 1 multiply. And in general, by the way, multiply used to be a very expensive instruction. Nowadays, there's enough hardware resources that it takes about 3 clock cycles, so it's not a huge deal. But anytime you can take 3 multiplies and use just 1 instead, that's generally a good idea. Question?
Isn't this optimizing for runtime, though? What if you're trying to optimize for space instead?
So the question is, what if you're trying to optimize for space? And there are a lot of optimizations that will make your code be bigger at the expense of, in order to go faster, right? This one, though, I'd argue this is actually shorter code, right? I mean, just look at the number of instructions. So, and usually, so code, that used to be a bigger concern when memory was sort of, back the original IBM PC had 640 kilobytes of memory, so in its maximum configuration. And that was a big deal to actually buy it that much. So, back then that was a big deal, memory. But nowadays, memory, the size of the program is usually a pretty small fraction of what you're dealing with overall. But it's a valid question. OK, so that just shows you an example. And in general, compilers are pretty good at doing those low-level optimizations like that if you write the code in a way that's reasonable. But there's some other ones that the compiler, and even the fanciest compiler you can buy, might not be able to figure it out. And so I like to illustrate this with when the first term we ever taught 213, I was looking at some lab code that some of the students wrote, and I was horrified about this code. And I showed it to the TAs, and none of them figured out what was wrong. And I've shown it to many other highly trained C programmers, professionals. And they go, looks OK to me.
I would hope the compiler could optimize away the subtraction here. A minus A. The only thing I can see here is maybe there's an off by 1. So say you have a capital A, it would be capital A oh yeah. Say you have a capital A, it's literally saying, hey, Can I rearrange the operation? I think I can. So it'd be a minus a, which would be 0, then minus a here. Could be a precedence thing. No, because we force precedence with the parentheses. It's something to do with this line, I think, because these the for condition and the if condition are pretty solid.
So let's figure out why I'm horrified by this code. So the idea of this code is supposed to be pretty straightforward. There's a string S, and I want to convert that string, all the characters in it, to lowercase. So I'm just going to read through the string, and for each string position, test that character. And if it's somewhere between uppercase A and uppercase Z, then I'm going to shift it to being between lowercase a and lowercase z. Otherwise, I won't change it. So pretty straightforward. But if you run this, you see that if you go up to 500,000 characters, which might sound like a lot.
So it's correct. So I think it's the subtraction. You're doing extra subtraction. That's not necessary because the compiler couldn't figure it out.
But it takes 240 or so 4 minutes to run this code. And you go, well, that's a pretty big string. It's really not a big string. You should be able to do lowercase conversion of a string in a lot less than 4 seconds. And you also notice this growth is nonlinear. It's quadratic. It's growing as the square of the string length. So this is not good. And unfortunately, it's the kind, and by the way, this is one of it's very easy, surprisingly easy to have programs that have some hidden performance bug that makes them run quadratic. And you run tests, and you test for strings of 10,000 or less, and it doesn't look like a big deal because the runtime is insignificant. So, but then all of a sudden, it hits a really bad case. So this is there's something wrong here. So what's so bad about this program? Well, the key is when in a test like this of calling strlen, so the way it's determining whether it's reached the end of the string is by calling strlen to figure out how long the string is. And now, and remember, if we do the
this third line is evaluated every time. Huh. That's funny.
For loop into a go-to form like you've seen. There's various ways to convert it, but all of them, the test gets built into the loop. So the main feature of that is this call to strlen will happen every time you go through the loop. And people overlook that fact. When you look at the different parts of a for loop, the initialization only gets executed once, but both the test and the update get incremented, get applied every time you run through the loop. So that's getting called as many times as there are characters in the loop, in the string, right? And now, how does strlen work? Remember, in C, the only way you know how long a string is to step through the whole thing and find the null character at the end. So strlen itself is a linear time operation in the string. And you're doing that, and so you're doing n calls to a function that takes time n. The string's getting shorter as you go, but not very fast. So basically, that's quadratic performance. And that explains why you get that runtime. So in particular, if I just make the following little change, I introduce a local variable called Glenn, and I pre-compute strlen because the length of the string isn't changing. I'm just changing the characters in the string. So the program will do the same thing, but now the runtime is so short it doesn't even show up. It's maybe a second to do 1 million characters. It's just not a big deal at all, as it should be. It's just running through. And so that's just an example, one of many that I've seen in my career where something that seems almost insignificant turns out to be a serious performance problem. So why couldn't a compiler figure this out? Why couldn't a smart compiler look at the original code and say, this is what the programmer wrote, but I know a better way to do it. I'll pre-compute strlen in advance. Well, there's a couple of reasons. One is, actually, if you look at the code for strlen, you see that it's actually modifying the string, and strlen, the code here is modifying the string, and we're calling strlen on it. So you'd have to be pretty careful to do the analysis, the compiler would, to figure out that even though the string is changing, the result you're going to get from strlen is not going to change, right? So that's one reason. And the second is, well, and how can the compiler be sure which version of strlen is actually going to get used? You remember in C, each of the files gets compiled separately, and only afterwards does it all get brought together in the linking phase, and some of that even happens after the program gets started. So even though there's a standard strlen function, it's not necessarily the case that that's the one that will actually get used in the final program. So the compiler really can't be sure of that. In particular, imagine I provided a sort of customized strlen function like this that is keeping track of the sum of the lengths of all the strings that it's been called on, or some other side effect like that, that program would produce a very different result than if whether or not I make the optimization. So the compiler has to assume that strlen is just a black box that does whatever it does, and can't make any assumptions about what side effects it might have and so forth. So it won't make that optimization on any machine, even with the best compiler. So that's just an example that, you can tell that I've gotten kind of sensitized to this so that I spot these, but a lot of people don't. So let's look at this. Let's see. What am I looking at now? Oh, this is another bad example, a bad coding example. Imagine I want to compute for a two-dimensional array A and a one-dimensional array B. I want to make B sub I be the sum of all the elements in row I of A. So again, this is a fairly obvious kind of way to write this program, that you say, well, bi equals 0, and I'm going to just accumulate it. I'll step through the row and accumulate all the values. And of course, we know now we could improve this by moving I times n out and so forth. I'm not trying to illustrate that. But what you'll see in the program, this is in the inner loop. And we've looked briefly at some floating point instructions. And remember, the main feature of them is the move instructions look like the move ones you're familiar with, except when we put floating point data in one of these XMM registers. So the main thing you see here is it's reading from memory, it's adding something to it, and then it's writing back to memory. And what that memory location corresponds to b of I. So what it means is every time through this loop, it's having to do a memory read and a memory write of b, in addition to the memory read of a. Even though presumably b of I is the same value that you just updated it to in the previous execution of this loop, right? So why do you read it, why do you write it out and then read it back in, increment it, and then again copy it back out? Why does it have to keep jumping back and forth between memory and registers over and over again? Well, the reason is because in C you can't be sure that there isn't what's known as aliasing, and I'm demonstrating it here. Imagine if row B is just declared to be okay. So imagine, and you can do this in C, this is legal C code, you can make one memory data structure overlay another data structure. That's referred to as aliasing, when two sort of separate parts of the program are referring to the same locations in memory. And the C compiler has no way of knowing whether there's a lot of work in optimizing compilers to detect aliasing possibilities. But in general, it has to assume aliasing might happen. So imagine this aliasing happens so that array B corresponds then to this row of array A. Then, of course, its initial value is 4816. But if you trace through what this code will do, it has this sort of odd behavior that is probably not useful for anything. But it just demonstrates that what will happen is, as as B gets updated, it's effectively changing A, and it's changing then what's being read during the summation. And so this is a real possibility in C. And so the compiler, when it's given code like this, it has to assume that these two memory locations might overlap each other. So that's why it's carefully writing it out and then reading it back in over and over again. And so if I just rewrite this code by introducing, again, a local variable and accumulating in that local variable, and then only at the end do I assign that to b sub I, then you'll see this exact same loop all of a sudden gets a lot simpler. It's just a read, floating point, read, and add to do that. And we'll see, in fact, the memory is actually one of the limiting performance limiters in a program. So this will be significantly faster. And again, that's something that you as a programmer would hardly think is a big deal. But the C compiler can't do that in general because it can't determine in advance what possible aliasing there can be. So as these two examples say, sort of get in the habit of introducing local variables and using them. And it's your way of telling the compiler, don't call the same function over and over again. Don't read and write the same memory location over and over again. Just hold it in a temporary one. And then it will automatically allocate a register and store it in that register, and everything will be good. OK, so that's sort of the kind of what we call optimization blockers, the kind of things that you as a programmer can make a difference on. And the main blockers are memory referencing, aliasing, and function calls, and sort of understanding what might happen in that function. So now what we're going to do is transition. Question.
Yeah. Two quick questions. So on the memory aliasing slide, there's this declaration of double B of array of size 3 equals A plus 3. This doesn't quite seem to be valid C code, because I think C2 makes a distinction between array and pointer.
No, this is valid C code. I'm sure this is valid C code because it ran. So this is initializing, calling it an array B. Remember, these are int stars. These aren't two-dimensional arrays, right?
Yeah.
So this is saying A is now a, think of it as a linear array of 4 elements, of 9 elements.
Yeah, I think that guy is right with the arrays. The aliasing. But let's just do his code exactly. So double A 9 is equal to just a bunch of 9 integers. Double B3, A plus 3. I hate that C tries to just cram everything on a single line. Like it's Clang format. This is gonna be double B3, and then A plus 3. Yeah, I mean he's right. Maybe it's a different version of C.
Demonstrates that what will happen can compile a lot of things.
C still makes a distinction between array and pointer.
No, this is valid C code. I'm sure this is valid C code because it ran. So this is initializing, calling it an array B. Remember, these are int stars. These aren't two-dimensional arrays, right? So this is saying A is now a, think of it as a linear array of 4 elements, of 9 elements. And A plus 3 is just to go in 3. So this is, it is declaring B is not a pointer, it's an array. But remember, with an array, you can use the name of that array as a reference to a pointer, a readable reference, not a writable reference, right?
But I'm currently using the GCC version 4.9 and just as invalid initializer.
Really? For this exact code?
Yeah.
Well, I'll double check it.
Oh, and also like a few slides before on the C style strings, is there a reason that this design of the C programming language use null-terminated strings instead of like Pascal-sized strings?
So the question is, why does C use null-terminated strings? And it does, and it might be a bad decision for multiple reasons, right? But I think in general, think of C was somebody who had, or a couple of people who had been writing a lot of assembly code and wanted to lift up that level so they weren't writing the same stuff over and over again, but not thinking in terms of how can I be the most abstract possible. So they were trying to provide sort of a minimum layer on top of machine level programming that would let them write code that could run from one machine to another. So in everything they do, they sort of use the most simple representation and don't assume any kind of, there's no array. Most languages would have array bounds checking, and array would be a data structure that would include its size, range of values and stuff. And C just doesn't. So everything about C is sort of the minimum. And it's been around for 40 or something years. So.
But like I believe Pascal kind of precedes that.
So this guy was right in his original question, but you shouldn't interrupt their lecturer like this.
No, Pascal does not precede C. No, that's simply not true. Pascal was created as a language for teaching by this fellow named Nicolas Vert. And it was very much an instructional language. So it was really designed to help students who needed help. And C was designed by professional programmers to let them write their code and not get in their way. So they're very different theory between the two languages, right? Yes?
I think the reason that was wrong is because you had like extra brackets at the end of the weight.
What's that?
You had extra brackets. After the 16, I was second bracket, there's an extra bracket.
I'm sorry. Oh, yes, that's a mistake there. I'll double check this, or people could check it. I'm pretty sure this code is okay, though. If not, you could certainly say double star b equals a plus 3, and that would work, right? Question?
Second element of B is 28, but not 22.
You think what?
After you call the function, the second element of B is 28.
You think this is 28?
Yeah.
Well, I'm not going to try and hand execute it here, but let's check it. You and I will check this code out, and we'll fix it if it needs to be fixed, okay? Thanks for pointing it out. Yeah?
Is it because when you do this, the array gets stack allocated as a local array instead of on heap?
No, that doesn't make any difference. In this,
So that guy was right about Pascal being older than C as well.
code? No, where it's allocated makes no difference at all here. So I'll check. That might have to be double star b equals a plus 3, but this was a while ago that I wrote this code. I'll double check it though. Okay, so anyways, that's the sort of end of the story for simple and they are simple optimizations. It's just you have to get in the habit of doing it. Okay, now what we're going to do is go a little bit fancier than this. And as I said, this becomes somewhat more system dependent, but pretty much nowadays all processors have similar implementation. They all do what's known as out-of-order execution, except for the most primitive microcontrollers. And so this is the kind of optimization I'll show. You'll find this general approach will work across quite a variety of machines. So what I'm going to do is do this by a series of examples, starting from some not very efficient code and making it run faster and faster. And we'll get a speed up of around 40 just in doing what we're doing. So I'll start by saying, well, assume I have a data structure that looks like the way Pascal implements arrays. Sorry, I have nothing against Pascal. We used to teach it back in the old days. But So a typical way you'd implement an array in a language is you'd provide both the values that are stored in that array, and then there'd be other information associated with it. For example, what size it is. And so this is sort of the sort of nice abstract way to do it. And you'd write code that makes sure that if you ever try to exceed the bounds on the array, you'd return an error signal. And so this particular function you're seeing is when I want to retrieve an element, I pass a pointer, and then that value, the pointer gets used to retrieve the value from the array. And the return value of this function is then just 0 or 1, 0 meaning failure and 1 meaning success. And I'm writing it in this way that I use a data type I'll call data underscore t. And that way I can run this, I can compile this code using different definitions of data underscore t to get ints, longs, floats, and doubles. And we'll see how the performance characteristics of those shift with the different data types. And the benchmark performance characteristics of those shift with the different data types. And the benchmark I'm going to use is a fairly simple one. It's just for an array or one of these vectors, I just want to combine all the elements of it, either compute their sum or their product. And again, I'm going to use macros here, ident and op, and define those so that op is addition and the identity value is 0, or the op is multiplication and the identity element is 1, so that I can compare addition and multiplication. So that gives us sort of 8 possibilities here, 2 different operations and 4 different data types. And so this is written in the sort of most straightforward manner, that I'm using this function called getVecElement to retrieve the successive values of this array, and then performing this operation on it. So now to express performance of this, we're going to use a metric I introduced called CPE, which stands for cycles per element. And the idea is that usually when you write code that, say, steps through a vector, anything that has sort of some linear performance as you get bigger, you don't really want to know for exactly, it takes this many seconds or microseconds or nanoseconds to do an operation. You kind of want to know often more what's its overall performance characteristics. And also, it turns out when you're doing low-level code optimization, it's much more useful to think in terms of clock cycles of the inner clock of the processor rather than an absolute term such as nanoseconds. Because whether a processor is running at 2 gigahertz or 2.3 gigahertz, I have no control over that as a programmer, but I can control sort of at the low level how many clock cycles are being used for different parts of the computation. So that's why it's called cycles per element. And you can think of it as, and this shows some actual measurements, that typically a function like this what I showed, the combine, will have some overhead, fixed amount that's associated with setting up the loop, doing the top level call and all that stuff, and then some component that's linear in the size. And so what I want to know is the slope of that linear component. And that will determine, that's what I'll call the cycles per element. You can think of the slope as the sort of incremental cost of adding one more element to the array. So now if I run this function I showed you, and I'm only showing, mostly only show 4 results, because it turns out whether it's int or long or float or double is not going to actually have any effect on performance for most of the cases. So if I just run this code through a compiler and don't do any optimizations, it takes around 20 cycles per element. And if I turn on optimization level 1, which is sort of the first serious optimization, it takes the time in half. So I'm down to 10 clock cycles per element just by changing the compilation. And that's using the most unoptimized code I could think of here. And then I won't go through it all, but using sort of the kind of things I described earlier, of sort of cut away some of the redundancy in this program, you can get it down to something a little bit simpler. And so one thing, instead of, you saw before, I was making a call to this getVec element, and every time it did that, it went bounds checking. And it's kind of silly to keep bounds checking the same array over and over again when I'm using its length as the determinant of how many elements to access. So if I'm willing to sort of forego bounds checking, what I can do is introduce a function that will just give me the actual data storage part of this vector and skip over all the other stuff. And so I can write a loop and I introduce local variables and all the kind of things we described. And accumulate in temporaries and things like that. Then the program actually gets a lot faster. Again, everything from here out is optimization level 1. And so it drops it down to a little over a clock cycle for integers, addition, or 3 clock cycles up to 5 clock cycles for double precision multiply. So that's pretty good. I've sort of definitely improved things. But the question is, well, is that the best there is? And also try to understand, what is it about these numbers 3, 5, and this seems to be something close to 1.25. So where are those numbers coming from? And does that indicate some fundamental limitation in my program? Well, in order to do that, you have to have some understanding of the underlying hardware. And there's a really good course you can take. I think it's called ECE 741 that will tell you everything you ever could imagine wanting to know about processor design. And you actually design processors like this. But I'm assuming you're not going to do that for a while, because you have about 7 prerequisites to do before that happens. So let me just give you the simple version. And this is sort of an idea of what a processor has looked like since about 1995. So this is old stuff, but it's enough actually to really understand it. It's so hard. It's really, the details are pretty massive. And so it's not even taught. For example, 447 is the ECE is the computer architecture course, and they don't really go into this kind of design here, because they're pretty hard. They're actually hard to design on your own. But the basic idea is, you think about a program as the computer just reads in an instruction, does whatever it says to do, reads in another instruction, does what that says to do. And that has nothing to do with how programs actually execute. What they've built up is this massive hardware infrastructure to make a program run way faster than it would if it were just doing one instruction at a time. And it employs a technique that's called superscalar out-of-order execution. And the idea is, roughly speaking, it takes your program, if you think of your program as a linear sequence of instructions, and it just sucks in as many of those as it can, and it pulls it apart to realize that certain operations don't really depend on each other. So I can start one even though it's later in the program than the one I'm working on right now, because they're independent of each other. And it's extracting what they call instruction level parallelism, places where even though your program is a linear sequence of instruction, buried in there is actually a sort of forest of different computations that need to be done, some of which depend on each other and some of which don't. And then it has a bunch of hardware. And so that's up here. This upper part shows this idea of fetching instructions. So there's a cache memory, a high-speed local memory that is just pulling in your instructions as fast as it can. And those instructions are then feeding a big pile of hardware that will extract out of it these low-level operations and figure out which ones depend on which others. And then there's a set of functional units in this part of it that are able to perform these low-level operations, to do arithmetic, floating point operations, to read data from memory, to store data back to memory, all using a cache, which is something you're going to learn about fairly soon, what all this cache is. But think of this as a high-speed copy of some of the data memory. And so what this logic tries to do is keep forking out, spawning off operations based on your program, and keeping these as busy as they can be, doing different fragments of your code, doing different instructions in a different order from before. And it turns out, you think of a register as the set of registers is a part of memory that get read and written. It turns out that in executing, a register now just becomes the name of something that one instruction produces and some other instructions consume. It's a destination for some, it's a source for others. And this whole bunch of stuff here just sort of magically passes the results of one computation to the input to another computation based on register names without ever storing them in an explicit register file. There is a register file. When things kind of settle down, they get stored away. Anyways, there's a lot of stuff going on here. But the main thing to think about is your machine has resources to do multiple operations all at the same time if you can somehow structure your program so that those can all get used. So this is, as I mentioned, it's called a superscalar processor. Is one that can do more than one instruction every clock cycle. And actually, Intel started in '93. The very first Pentium could do 2 instructions at once. But then a little later, they came out with one called the Pentium Pro, which is sort of the basis of all modern processors. And the lead architect, by the way, was a CMU graduate. This out-of-order execution is the model that's used nowadays. So the other thing is those functional units are more complex than you think they might be, in that they have what's called pipelining. And the idea of pipelining is, imagine you can break up a computation into a series of distinct stages. A simple example is if you want to compute A times B plus C, you first do the times and then you do the plus. But it actually gets deeper than that. You can take something like multiplication and break it up into smaller steps that can be done one after the other. In a way that, and then if you have a separate dedicated hardware for each of those stages, then you can do what's called pipelining, which is when one operation moves from one stage to the next, a new operation can come in behind and start its thing. So this example shows, imagine I had a 3-stage pipeline multiplier, and I want to do this computation, A times B, A times C, and now multiply those together. So the thing to observe is that A times B and A times C don't depend on each other in any way. So I can do them both. And I don't have hardware to do them simultaneously, but I have them enough to do one right after the other. So I can feed the first computation into the first stage, A times B, on time step 1. And then time step 2, it will move on to stage 2. And time step 3, it will move on to stage 3. But now I can start A times C in the time step 2, because this stage became available once A times B moved from stage 1 to stage 2. And so I can follow right behind, just one clock cycle behind this other operation. Now, P times 1 times P2 obviously depends on both of these products. So it can't start until A times C is completed, and then it will run through the pipeline without anything else. So overall, then, we've done what would have normally seemed to be 9 steps worth of arithmetic in a total of 7 steps here because of pipelining. Question?
If there is more than one floor, would it be possible to do 2 stages at the same time?
If you had, like in this picture here, if there were different multipliers in these different places, yes, you could do those 2 completely independent of each other.
So it's like core, like would all those like multipliers and everything, is that like what would be in a core? Is that
Yes, this is all in a single core of a single processor. Multi-core is yet another. This is a lower level parallelism than you get through multi-core. And it's present, except in the sort of lowest end, lowest powered embedded processors, some version of this exists. And most of the time, your hardware is not being fully utilized, is one thing you're going to learn from this. So that's the idea of pipelining. It's sort of like parallelism, but it's not that you have multiple copies of resources. It's that you have this ability to stream operations through a single hardware resource in close succession to each other. And so Haswell, which is a little bit more recent than the Shark machines, but not that much more, is one of the most recent versions of the Intel x86 series. And the functional units include, there's a lot of functional units that can do different things, but when you add it all up, there's a possibility of it doing 2 loads in 1 store, 4 integer operations, 2 floating point multiplies, 1 addition, and 1 division. They can't all happen at the same time because there's some are share functional units. But the point is there's really a lot of equipment there that can do stuff. And also, you can measure how an instruction now has 2 characteristics. An operation is how long does it take from beginning to end, but also how closely spaced can 2 operations be because of this pipelining. So you see that most of them take some number of clock cycles to perform, but they're also pipelines so that you can do a series of them just 1 cycle apart. The only different ones that aren't is you'll notice the division is both very slow and it's not pipelined. And division is a very expensive operation on most machines, relatively speaking. So what I claim then is these characteristics then provide a limit on how fast our program can run, our original program. In that I have a series of multiplications, for example, of integers here. And this shows the code for it. And the result of, I need the result of 1 multiplication before I can begin the next. So there's a 3 clock cycle bound here. And you'll see that, in fact, my measurements all correspond to what I'm calling the latency bound of these machines, which is just based on how much time it takes from a beginning of an operation to the end. And the reason is we can sort of diagram the computation being done by this program, that it's doing a series of multiplications, and I require the result of 1 multiplication before I can start the next. In general, if you look at this loop code, it has to compute ECX, the updated value of it, before it can now start the next one. And so that's why, even though I have a pipeline multiplier, my program itself limits me to the sequential execution of all the multiplies. So let's see if we can't get beyond that bound, that latency baund. Well, there's a fairly common technique that you might have heard of before that's called loop unrolling. And the idea of loop unrolling is just that you, rather than executing one value within a loop, you execute multiple ones. And so this code shows unrolling by 2. And what it says is I'm going to step through this array 2 elements at a time. And within each of the inner loop, I'm going to combine the values from di and di plus 1. And I have to put in some extra code to finish off what happens if the original array was of odd length. But you get the idea. And this idea, I show this code of 2, but you could imagine this applying for different values of loop unrolling. So will this help us any? Well, when I run it, I get that the integer addition got a little faster, but the other ones didn't improve at all. So this one is going faster because basically the old code, just the overhead of the loop indexing and incrementing was enough to be slowing me down because it's already close to a clock cycle. So I just managed to knock that down to be at the latency bound of this particular instruction. But it didn't improve the other ones because I still have this sequential dependency. In order to get my new value of x, I have to first do one computation and then do the other before I can begin another one. But this shows me the way I could make a very, very small change and change performance fairly dramatically. What if I take these parentheses and shift them to the right? Would that make any difference? And lo and behold, yes, you find that, and I'll call that transformation unrolling by 2, computing one element at a time. I'll talk about that in a minute. But I'll use this lowercase a to say I've done an associativity transformation. And you see, all of a sudden, my time's dropped in half for these 3 cases. So something's going on. And so let's see why that is, and now I'll introduce it. And so if I take my picture from before and think about what those computations imply, you'll see that right now I've changed the structure of the computation so that I'm pairwise combining each pair of elements of the array and then accumulating those into the overall computation. So I've actually, that shifting of the parentheses fundamentally changed how I'm doing my computation. And you can see now that this critical path, which is what determines, in this case, the performance limitation, just got shorter by a factor of 2. And that's why I'm now running twice as fast for the operations, not for integer addition, but for the other 3 operations I've cut by a factor of 2, just by that shift. Now there's some good news and bad news here. The good news is if this is integer arithmetic, we know already, you know that 2's complement arithmetic is associative and commutative. So it really doesn't matter for both multiplication and addition. So it really doesn't matter what order I combine these elements in. I'm going to get the exact same answer no matter what. But you also saw for floating point that's not the case. So with floating point, that shifting these parentheses, because of rounding possibilities and even potentially overflow, you might get different values, results from these computations. But then again, if you think about, is that really going to happen? Chances are no, that it's not really going to affect the outcome of your program. But it's enough of a change that most C compilers, or most compilers, period, will not make any change that changes associativity, because they're very conservative when it comes to floating point. So that's something you as an application programmer has to know well enough. Is this a valid can I do this transformation without messing things up? And now what I'll say is now there's a new set of bounds. So a bound is what would appear to be sort of the best you can do based on some constraint in the program. And before it was saying, well, the latency, the total time through for a given operation was a bound. And now I say, well, there's an even more fundamental bound, which I'll call the throughput bound, which is just based on I only have so much hardware out there, and I can only pump it so fast. So for example, these two, the throughput bound is 1 because I only have that actually becomes limited by the requirement that I'm having to read from memory, and I have 2 different load units. Oh no, I'm sorry. I only have 1 multiplier for integers and 1 for addition. The throughput bound for these 2 actually is just a half, because it turns out there's some odd part of the hardware design that has 2 floating point multipliers, but only 1 floating point adder. And we'll see that we can actually make this multiplication code run faster than addition code. And over here, again, my limit will be that I only have 2 load units, and I have to be and I have to read for every element I'm computing. I have to be reading 1 element from memory, so I can't get below that. Okay, so but we saw this transformation now has let us break out of this latency limitation and get something closer to throughput. Here's another technique that can be used to, again, sort of get more parallelism going. And I call this multiple accumulators. And the idea is, let's imagine that we have the odd numbered elements and the even numbered elements in the array. And we can compute separate sums or products of those 2 sets of elements, and then at the very end combine them together. So this is another form of an associativity transformation. We're changing the order in which we combine things together. It's just that we're doing it in this sort of odd-even manner, or in general, every ith value if we do it by some parameter I. And it has the same issues that if it's integer arithmetic, it's fine. If it's floating point, there's a risk of changing the behavior of the program. But you'll see that, again, we get a cutting in half here and a little bit below 1 for integer addition. And again, we can think of it by looking at these pictures of what gets computed. And you see what we're doing is we're computing here are all the even numbered elements being combined, and here are all the odd ones, and then at the very end we're combining those together. And so we can generalize this. If we can unroll by a factor of k, of L, and we can accumulate k results in parallel, and we can use various values of L and k for it. In general, L has to be a multiple of k. And so you run it out, and you can get, for floating point multiply, you can actually get it down almost to this throughput bound of 0.5. This is incorrect. This is integer addition. That should say int addition. You can, again, this is incorrect. This is integer addition. That should say int addition. You can, again, get it down to around 0.5. And in general, by sort of picking the best parameters, I can get very close to the throughput bound of this processor. So I've been able to take something, remember it originally was 20 clock cycles, then 10, and now I'm getting it down to 1 or fewer clock cycles per element. So now, just as the final step is, okay, is that as good as it goes? Actually, no. You remember when I talked about floating point, I mentioned that there's this special set of registers that are on a x86 that were called XMM registers on the Shark machines. And now this Haswell, this newer generation, have something called YMM registers, which have the feature of being twice as big as XMM registers. So in particular, these registers are 32 bytes long. And there's a new version coming out within a year or something. They call it AVX 512, where the register is 512 bits, so that's 256 bytes long. No, it's 512, excuse me, it's 64 bytes, right? 64 bytes, so it'll be twice as big as these. And as I mentioned before, you can think of these as a way of operating on 32 individual characters, or I can treat them as floating point. And we saw before that nowadays the regular floating point makes use of sort of the low order 4 or 8 bytes of these registers. But there's also instructions called vector addition, where one instruction has the effect of doing 8 floating point additions at once on float data. And on double precision, its counterpart does 4 of them at once on these. And that hardware is there. It's just sitting there waiting to use, and it seldom gets fired up to really make use of it. But so that floating point multiplier that can do floating point multiplication in 3 clock cycles and is fully pipelined can actually do 8 floating point multiplications in parallel and pipelined in 3 clock cycles. And as I mentioned, the Shark machines has an earlier version where the numbers are half of these. So it can do 4 single precision or 2 double precision at once. And if I write code that uses that, what I call vector code, then you can see I can drop by a factor of about 4 across the board here and make it run much faster. So this 0.06 is really 0.0625, right? It's doing 16 operations per clock cycle on that. Can't quite hit the vector throughput bound, but in general, making this thing run much faster. And so the people who really worry about, and you can imagine these instructions were introduced for things like video processing, image processing, sound, sort of signal processing where performance really matters. How fast you can display an image, how fast you can rotate something, how fast you can perform graphics makes a big difference. In video games are one of the big drivers, but even for sort of other operations you might do on images. And so these instructions were really designed to do it. And people who write code for those kind of applications get pretty good at writing code in a way that they can do this what's called vectorizing. And unfortunately, so the Intel compiler will actually automatically do some of this for you. GCC, they attempted to implement it, and it didn't work very well, so I think they discontinued it. It turns out there's a web aside. So this is on the web from the book's web page that describes how to do this programming if you're interested. There's extensions to GCC that are very funky, really weird stuff. But you can write code that then will get compiled down to make use of these kind of instructions. And that's how I did it and how I got these performance results. OK, so that shows you if you really want to, but that's very machine specific. That will only work on, well, you can actually tune it so it's easy to compile it to go between different machines, but it's still fairly specific and very specific to GCC, in fact. So that sort of shows you, though, if you really want to push it, what you can do. Now let's get back to one of the things I told you about how you can, if you think of your program as a very long linear sequence of instructions, then the thing is trying to grab as many of those and pull them apart as fast as it can. But of course, you know your program is actually typically a loop, and there aren't many instructions in that loop. So how is it turning that into a linear sequence? Well, that relies on an idea of how do you handle branches. So typically, the program fetching ahead, grabbing instructions, and it will come to a branch instruction, a conditional jump of some sort. And there it has a dilemma, because in general, this branch could either, be taken, meaning it will go to the branch target, or it could do what's called fall through, meaning the test fails, and so it just continues execution. And there's no way a priori to know what will happen. These can often be data dependent. And so the way this is handled on a modern processor is by doing what's known as branch prediction, which is essentially just guess. Which way is this branch going to go? Is it going to be taken or not? And you predict, and then you start executing along the predicted direction, but do it in a way that if you make a mistake, you haven't caused irreparable harm to the program. And we'll see what that means. So what really happens then is up here, there's a lot of logic that's trying to suck out instructions. And then there's a branch unit that's basically coming along later and saying, yeah, you're OK. You predicted that correctly, so you can keep going. Or it will throw up a flag and say, uh-oh, wait a minute, stop. You mispredicted this branch way back 100 clock cycles ago. Well, it's not that long ago, but some number of clock cycles ago. You've got to fix it. And so the handling of jumps then becomes more a case of guessing up here and then either confirming or denying that guess down below. So in general then, it will predict it one way and begin executing. So imagine, for example, in a loop like I've shown you, that you predict that the branch will be taken, that you'll go back to the start of the loop again. That's actually a pretty good guess. It's a good guess until you hit the end of the loop. But let's just guess that way. And so the program will just keep guessing that the branch will be taken. And by that means, by all those guesses, basically create this long linear sequence of instructions that can be pulled in and executed. And in general, some of them will be fetched, and some of them you'll actually have done the operations that are called for in the instruction. And then what happens is if the flag goes up to say, no, this was invalid, then what will happen is it will go back and cancel all the instructions that have been fetched and executed. And the way it does that is, you'll notice all these instructions only modify registers. And it has multiple copies of all the registers going back. These are the values that I'm sure of. These are sort of speculative values, pending updates to them. And so when it comes time to cancel, it just cancels out all those pending updates and goes back to values that it's certain of. Question?
Where does it store the multiple copies?
There's a big block they call the register renaming unit, which is sort of multiple copies of all the registers as they get accumulated.
Why can't you store different data in the multiple copies? Like, why does it have to be the same data? Don't we potentially have more registers?
Oh, it has many more. It will typically have several hundred of these sort of virtual registers to keep pending copies to the actual registers.
So why can't you store different data?
It does. It stores, here's the old value, here's the first update, here's the second update, here's the third. And it keeps track of all you can imagine why this is not something you learn in a one-semester course, right? That to keep track of all those different things flying by and make sure that it works is a pretty tricky business. But conceptually, it's a pretty simple idea that it just races off, does a lot of things based purely on speculation, And then only if it makes a mistake, it goes, uh-oh, and it sort of rolls back to as if it had only executed up to a certain point. And then it moves forward and starts in going the correct way. So, and it can get away with this. It's very interesting and tricky stuff. But you remember we talked early in the course about the difference between using conditional moves and conditional jumps to implement conditional operations. And conditional moves can take place totally within the structure of this pipeline. But a conditional jump, if it's an unpredictable branch, the problem is it might go off executing and do a lot of wasted work, but even worse than when it gets back and has to restart. It takes a while to sort of fill up all the buffers in the system and get the whole thing running at full steam ahead. So that kind of finishes up then the way I describe it is, first of all, don't do anything stupid. And stupid is probably too strong a word. Don't do, sort of keep in mind there's certain things that you should as a programmer be doing all the time. And they're not obvious, perhaps. And then begin thinking about tuning and getting some of the instruction level parallelism. And I describe it as for the machine, but as I said, pretty much all processors nowadays, it's a class of machines. And so these general techniques will work, those ideas of changing the associativity, they'll work whether it's the ARM processor built into my cell phone or the x86 processor built into your laptop or one of the Shark machines. They all have the same general implementation structure. So these techniques will work across all of them. OK, that'll do us for today.
Okay, I'm gonna end here today. Bit of a short day for me, just about 5 hours, a little over. Got a lecture done, finished the floating point chapter, did the practice problems in the chapter. Not a huge amount of progress, but certainly progress. And then we also went and read one of the webasides from chapter 3. We could just add in here that we watched this lecture on program optimization. Kind of curious if I want to go back and read all this stuff about the y86 instruction set architecture. It's going to be 387 to a lot of diagrams, stuff about pipelining. Three to 7 to a little over 100 pages. So they create this instruction set architecture. They actually have a encoding. Logic Design and Hardware Control Language, HCL. Stuff about logic gates. Don't really need to review. General principles of pipelining. That'd be nice to read. So much shit here. Yeah, I'm gonna skip this. There's a section of performance analysis. Let's see. We can read the summary. The summary has an aside, a web aside. Summary, we have seen that the instruction set architecture, or ISA, provides a layer of abstraction between the behavior of a processor in terms of the set of instructions and their encodings and how the processor is implemented. The ISA provides a very sequential view of a program execution with one instruction executed to completion before the next one begins. We define Y8664 instruction set by starting with the x8664 instructions, simplifying the data types, address model, instruction encoding considerably. Resulting ISA has attributes of both risk and CISC instruction sets. We then organize the processing required for the different instructions into a series of 5 stages, with the operations at each stage vary according to the instruction being executed. From this, we constructed a seek processor in which an entire instruction is executed every clock cycle. By having it flow through all 5 stages, pipelining improves the throughput performance of the system by letting the different stages operate concurrently. At any given time, multiple operations are being processed by the different stages. In introducing this concurrency, we must be careful to provide the same program level behavior as would be sequential execution of the program. We introduced pipelining by reordering parts of Seek to get Seek Plus, and then adding pipeline registers to create the pipeline. We enhance the pipeline performance by adding forward logic to speed the sending of the results of one instruction to another. Several special cases require additional pipeline control logic to stall or cancel some of the pipeline stages. Our design included rudimentary mechanisms to handle exceptions, where we make sure that only instructions up to the accepting instruction affect the program visible state. Implementing a complete handling of exceptions would be significantly more challenging. Properly handling exceptions gets even more complex in systems that employ greater degrees of pipelining and parallelism. In this chapter, we have learned several important lessons about processor design. Managing complexity is a top priority. We want to make optimal use of the hardware resources to get maximum performance at minimum cost. We did this by creating a very simple and uniform framework for processing all of the different instruction types. With this framework, we could share the hardware units among the logic for processor in different instruction types. We do not need to implement the ISA directly. A direct implementation of the ISA would imply a very sequential design. To achieve high performance, we want to exploit the ability in hardware to perform many operations simultaneously. This leads to the use of pipeline design. By careful design and analysis, we can handle the various pipeline hazards so that the overall effect of running a program exactly matches that would be attained with the ISA model. Hardware designers must be meticulous. Once a chip has been fabricated, it's nearly impossible to correct any errors. It's very important to get the design right on the first try. This means carefully analyzing different instruction types and combinations, even ones that do not seem to make sense, such as popping to the stack pointer. Designs must be thoroughly tested with systematic simulation test programs. In developing the control logic for pipe, our design had a subtle bug that was uncovered only after a careful and systematic analysis of control combinations. Y8664, so this is basically like an architecture that they created for their own little amusement and instruction for students. The lab materials for this chapter include simulator for the Seek and pipe processor, used similar S2 versions, GUI, text. Okay, I'm comfortable skipping this chapter. Yeah, definitely gonna do that. And he had one lecture on optimizing. And the next lecture is right into the memory hierarchy, which is like what I really wanted to get out of this book, was reading the memory hierarchy. This is about 70 pages for the optimizing thing. Something he said at the beginning of the lecture is like, we only have one lecture.
We've now gotten through all the lectures on machine code, and we're starting to talk about, okay, now that you know this stuff, what can you do with it? And this lecture is along the lines of that. This is sort of what you are now empowered to do now that you can look at and understand machine code. This material is a little, there's a whole chapter of the book, chapter 5, on performance optimization, and we're only going to do one lecture on it. And we don't have any labs, unfortunately, that really get you to push your limits on this, which is too bad because it's a very interesting topic and one I think you'd find yourself well equipped for. There are typically a few small exam problems that are sort of based on some of the material here you'll find in old exams. But really the idea is, how can I make programs run fast? Given that I've sort of know what algorithm I'm using and I've perhaps gotten a program that runs, how can I make it run faster? And we're only going to do one lecture on it, and we don't have any labs, unfortunately, that really get you to push your limits on this, which is too bad because it's a very interesting topic and one I think you'd find yourself well equipped for. There are typically a few small exam problems that are sort of based on some of the material here you'll find in old exams. But really the idea is, how can I make programs run fast? Given that I've sort of know what algorithm I'm using.
All right. Yeah, let's go ahead and flesh this out then. We'll go back to the contents. Yeah. And there's a section 5, or chapter 5. Just grab all these. In fact, I'll just grab everything. Paste it in there, please. There we go. Then we'll do the same thing down here. And then it looks like, was this 531? Oh, it's from there. Okay. So capable is expressing program, eliminating loops, reducing, understanding modern processors, overall operation. Yeah, so all this, we can just grab everything. Just go up here and let's see, 7, 3 there. Okay. They have a section on profiling. I really do want to read that. Okay, I'll be reading this. I'm not gonna do the practice problems, but I will read it. I'm gonna hop off here. So tomorrow, I'm gonna work on the attack lab, and yeah, I'll start on that early in the morning. Just focus on the lab work. The last lab, the bomb lab, I did, was it last weekend? It took me an entire day because of all the GDB stuff. It was very challenging. So I'm unsure about the level of difficulty of this one, but I will hop on tomorrow morning and start on it. Since I don't have any gym in the morning or anything. And then I'm going to skip over the processor architecture chapter, and we're going to start in chapter 5. Cool. All right. I'll be on tomorrow. Later.